All right. Also, I want to first of all thank the organizers for having this very nice workshop and also having me here. My talk originally was actually oxides materials for spintronics, but when I see the limited amount of time, I decided to add a subtitle, a new road towards a low field and high temperature closure-magnetic resistance, just to make my talk a bit more focused. To motivate my talk, I will first give a brief look back at the development of the field of spintronics. In a broader sense, it all started actually in a very old time, like more than 100 years ago, 1857, when Lord Kelvin wrote a letter, to Proceeding of British Royal Society, talking about the observation of AMR effect, the anisotropic magnetic resistance. So meaning that in the 3D magnetic metals, the resistance depends on the angle between the field direction and also the current direction. So this actually later was understood as the origin of spin orbital coupling, but the real understanding actually it's only very recent years that theoretically from the spin polarized band structure point of view, people understand how the spin orbital coupling can really induce AMR effect. But before we understand the AMR, people have been using the AMR as a field sensor in many areas already. And until that, in 1975, there's another very important milestone work in the field of spintronics developed. That's the TMR effect, observed or reported by Juliet, talking about two magnetic layers when it's separated by a tunneling barrier. In his case, it's a semiconducting germanium, but these days, people usually using the oxides insulating barriers. But he talked about that when the magnetization are parallel to each other of these two magnetic layers, the resistance is lower, and if it's anti-parallel, resistance is higher. But the TMR and AMR, both in terms of magnitude, are very small. It's only like a few percent at room temperature. So no wonder that in 1988, there's this huge wave generated by Albert Ferd and Peter Greenberg when they reported independently in PRB and PIL about the observation of GMR, that these multi-layers of ferromagnetic metals and non-magnetic metals. So you have this much larger, actually order magnitude higher magnetic resistance. And that later, with the invention of spin valve effect by Stuart Parkin, finally in 1997, in 1997, that the IBM made the real device, right? This in all hard disks that rated as based GMR. And soon then people start to become a bit more ambitious, trying to make this GMR into MRAM. However, the GMR is a bit too small and the resistance is too low for MRAM application. Then there's a look back or this revisit of TMR effect. With first the theory prediction and then the experimental realization. Now these days, you can make a TMR at room temperature a few 100%. So it's large enough for the MRAM applications. As a matter of fact, that the MRAM is already in the market. That it's now these days are generating billions of dollars market, but still room to go. That to make it a real potential applications. So you can see that all these milestone works for the development of spintronics is the order magnitude increase of the MR, right? Whenever you get a order magnitude increase of magnetic resistance, you can really, generate some kind of major impact in the field. So that's why that there's a huge excitement when the CMR effect is reported, right, in the manganese, which is the old material that people know these materials in the 1950s. But then in the 1990s, there are two papers reporting very high magnetic resistance on the order of, you can see, even in the original report, it's already like, 4 orders of magnitude larger than GMR effect or the TMR effect, right? So it's a real large magnetic resistance resistance. So the reason that these materials can have such a huge magnetic resistance is because of the so-called electronic phase separation in these materials, meaning that in these materials, even for a single crystal, in the ground state, there's a coexistence of ferromagnetic metallic and antiferromagnetic insulating phases. When you apply a magnetic field, you can drive a phase transition from antiferromagnetic insulator to a ferromagnetic metal, leading to a percolation of the ferromagnetic metallic phase, and then giving rise to a very large change of the resistance. So this is so-called CMR, right? However, the problem for application, there are two. The first thing is that you really need a very large magnetic, somehow. Yeah, you really need a very large magnetic field to drive the antiferromagnetic to ferromagnetic phase transitions. And that's on the order of Tesla field. So that's too large, I mean, for any applications. Second thing is that the transition temperature is usually well below the room temperature. And that's also not very useful, I mean, in general application purpose. So these are the two problems that people have been working on, but with very limited success. So today my talk is going to show you that we are now actually at a very edge of making a breakthrough of these two problems and generating real low field and high temperature CMR effect in these materials. So this is the outline of the talk. First of all, I will talk about the origin of these electronic phase separations, because you really have to understand the origin, and in order to get this low field and high temperature CMR effect. And I'll talk about our effort of lowering the required field and also increasing the temperature above room temperature. And finally, I'll give you a roadmap how to achieve this low field and high temperature CMR. In fact, if you are first principle, calculation serious, then you already start to wonder that this is indeed a very strange phenomenon. If you have a single crystal, right, then the coexistence states of antiferromagnetic, ferromagnetic as a ground state is very strange, because usually energy-wise there has to be one of the state has the lowest energy. Right? How come the coexisting phases is the lowest energy state? So that's why there are many theories actually discussing from various aspects, but under certain models. Right? So the model probably is correct from theory point of view, but it's not necessarily catching exactly the sense about the experimental systems. But anyway, this Elbio D'Agotto, Alan Bishop, and Peter Littlewood, and many other theorists having reported about their theories about explaining the physical origin about the systems. And then they all like to use one of these model systems, the lanthanum pristinium calcium manganese O3. In fact, it is just a AbO3 perovskite, right? But on the A side, the lanthanum, calcium, pristinium ions actually are mixed together. So, they are sort of like randomly occupying these A sites. So that's how the crystal structure is. I'm not going to get involved in discussing about which theory is correct, but from an experimentalist point of view, we get into this problem. We look at actually some of these observations of the domains, of electronic phase domains. So the original report about this LP-CMR systems electronic phase separation was actually made by Song Chang in 1999, which he reported that the domain size is on the order of micrometer scale, right? But the interesting thing is if you take the pristinium dopants away, then you notice that the domain size becomes a lot smaller, becomes only 10 nanometer scales. So it looks like the pristinium dopants is very important. However, taking the pristinium dopants away is too much of action in the system. So we decide that instead of taking the pristinium dopants away, we just make the pristinium dopants keep the nominal doping concentration, but just rearrange the spatial location of the pristinium dopants, making it spatially ordered. The way you can do it is just using the, this superlattice growth. What you can do is you grow two atomic layers of LCMO, the lanthanum calcium manganese 3, and one layer of the pristinium calcium manganese 3. So you stack this together as a superlattice. So you make this nominal doping concentration exactly the same as this conventional LPCMO single crystal thin films. But the pristinium dopants now becomes spatially ordered at A site, right? So now you can compare these electronic phase separations. Now this, on the left-hand side, it's this conventional LPCMO thin films. The domain size is on the order of 1 micrometer scale, right? But now you can look at this pristinium spatially ordered LPCMO. Now this domain size becomes order magnitude smaller, right? But now in this material, the calcium dopants are still randomly distributed in A site. We can actually also make this fully chemically ordered by making a monoatomically stacked superlattice. One layer of CMO, one layer of LMO, one layer of PMO, right? So now you have actually fully chemically ordered system, right? All these lanthanum, pristinium, calcium dopants becomes spatially ordered. And what you see that there's absolutely no electronic phase separation. The phase system becomes a single phase. Of course, you can apply a magnetic field to make this whole system through a first-order phase transition, driving it from one phase to the other. But there's not going to be a coexisting phases, existing. So now we can actually, at least from experimental point of view, we can see a direct evidence that, these chemical dopants induced disordering is a real physical origin but this disordering is in fact, from an experimental point of view, it's intrinsic because there's no way you can, without doing this very special actions, you can make these chemical dopants spatially ordered, right? So this is the reason that any kind of disordering that will introduce these electronic phase separations to prove that we, in fact, even with this perfectly chemically ordered system, we just do a slight annealing, 20 degrees C above the gross temperature, then you will actually have some interdiffusion at the interface. Immediately, you will recover this electronic phase separation exactly the same as those LPCMO systems. So this is one way to prove that. In fact, you don't even have to using this chemical, interdiffusion to introduce disordering. You can just make some lattice, local lattice distortion that also introduce disordering. Will also leading to this kind of electronic phase separations. Again, this is this perfectly chemically ordered LPCMO system grown on S-type substrate. But through the cycle of temperatures, there's going to be a structural phase transition for the substrate from cubic to tetragonal phase. But when it's in a tetragonal phase, there's going to be tetragonal structural domain walls. That domain wall will go away when you raise the temperature to room temperature. But however, when the domain wall happens, it will actually introduce some kind of local lattice distortion in these superlattices. And the local lattice distortion will immediately leading to this electronic phase separations, where you can see we can simultaneously getting, or not simultaneously, but getting these magnetic images and also this conductive images of the same surface location. And you can see that these are the ferromagnetic phase, and the mixed phase, in fact, are the ferromagnetic and antiferromagnetic phases in this kind of domain wall boundaries. But these domain wall boundaries are also more conducting. So this is also a direct comparison of the MFM and MIM imaging, showing that these electronic phases are indeed ferromagnetic and metallic, if you can look at the same surface locations. So this is also thanks to AltoCube, for providing us these microscopes, and actually we're happy to use this, for looking at these images. Now, how are we going to reduce the required field? To make this high magnetic resistance, right? So the idea is that we study this evolution of these electronic phases as a function of magnetic field. We find that the field required to for the domain growth is much less than the domain nucleation. This is, I'm not going to show you the details, but we compared all these series of images, and then finally we can reach the conclusion that the domain growth requires much less field than the domain nucleation. So now the idea is becoming that how are we going to, introduce the nucleations without, external field? If we can do that, then we only need some small magnetic field, to boost this domain growth and reaching this CMR effect, right? So, and the way we can do that, in fact, from our old work, that we put the magnetic nanodots on a magnetite thin film. We find that the exchange field provided by the magnetic dots with the manganese spins underneath is enough. Actually, this is an enormous field, right, the exchange field, that can convert the regions below this magnetic nanodots into the ferromagnetic metallic phase. So you can see the effect is very dramatic. On the very top left, right, you can see this is the LCML film, which is in the antiferromagnetic insulating, state. You put the magnetic nanodots, they are separated, so they are not conducting, but they are enough actually to create enough of this ferromagnetic metallic nucleations. And this makes this whole film becomes ferromagnetic metallic with a very high transition temperature, right? So the effect is enormous. So this is the idea that you can use the magnetic nanodots through this exchange field to drive this, nucleation formation. And then you can use the external field, to boost this growth of these nucleations. And then you can really having, hopefully, the small field driven CMR effect, right? So this is a way to, drive this CMR effect with low field. Now, what about this temperature? We find that we grow these LCMO films on a tensile strain substrate. In this case, it's a STO substrate, right? So you can see this. This is the final, results. Just looking at certain doping concentrations, and then you can see this under tensile strain, the LCML film. The bulk cure temperature is about 220 K or so, right? But this LC film, real cure temperature becomes over room temperature. So we also understand that from the band structure, so it is because that the tensile strain leads to a very increased or this vertical coupling, exchange coupling. Of course, the lateral coupling becomes reduced, but the vertical coupling is enhanced, and that gives you to a larger TC in this case. So with all this understanding, now we have a strategy, right? A clear roadmap how to achieve this low field high temperature. We can grow the LCMO films on tensile strain substrate. So first of all, we have actually high cure temperature phase material, right? And then on top of that, we actually start to play around this magnetic nanodots deposited on top. You can change the density and also the size very conveniently. So you can play around these independent parameters. And then finally, you can let the system in the verge of this percolation, right? So the density is high enough that the system is very close to a ferromagnetic metallic phase, but not yet, because they're not percolated. And then you start to apply a magnetic field, then hopefully you can drive the system to this percolated phase with modest field. So this is how we are going to try to achieve. It's still ongoing work that for this. I hope that next time, if I'm still getting invited in this series of talk, I'm going to report about this low field and high temperature CMR effect. To conclude that, I talked about the origin of these electronic phases and how are we going to reduce the magnetic field and also increase the temperature for CMR effect. And so finally, I want to comment that our most effort, in fact, is using this electronic physics for many things. So this is why I talk about oxide spintronics, is that you can use it for this spin logic applications. You can also use it for neuromorphic computing and probabilistic computing. And these are all our major efforts of using these oxide materials, which computing physics, giving you a lot of freedom of play around under external fields. Before I close, I have to acknowledge my collaborators, my experimental collaborators at Fudan universities in the group, and also the series collaborating with Shen from Southeast University, China, Hong Junxiang from Fudan University, Lu Qianwu from UC Irvine, and Elbida Goto from UT. Thanks very much.